Hello and welcome to episode 2 of how to make a platformer in Bevy. In this episode, I'll be covering how to cut down on boilerplate in our games, and also how to reduce the duplicate code and clutter that comes from adding lots of systems to our game. This is primarily done by using plugins. If all goes according to plan, I will hopefully have an episode of Bevy Basics out covering plugins if you want to go watch that. The plugins that I'm going to primarily be using in this episode is Adding Rapier for the physics engine, and Leafwing Studio's input managing plugin to introduce a better way of controlling the player that doesn't require me to copy and paste the player's key bindings everywhere I intend to use them. I was also going to use Bevy ECS tile map, but I found that this was far too complicated for the implementation that I wanted, and I figured it'd be easier to implement my own tile management system since the ECS tile map plugin had far too many features that I would have to learn and is far too complicated for the scope of this project. The first thing I did in order to minimize the clutter in the application is move the animations into their own plugin and then into their own folder. This is fairly simple to do in Bevy. All you need to do is create a marker struct to contain the plugin's information that you can then add as a plugin to your application. When you implement the plugins tray onto your struct, you then have to provide the build method. This takes in a reference to the plugin struct so you can contain configuration information and a mutable reference to your application. This mutable reference then allows you to do any manipulation that you would do on the application itself, but inside a plugin in a contained way. So if you have a bunch of systems that rely on the other systems being present, you can add them all in the same plugin, allowing for the system to run without you needing to have to worry about informing the user that they need to include multiple systems. To make my animations into their own plugin, I add the animation system and the changing the player's animation system onto my application inside the plugin, and also make sure that the animations resource is initialized. Since this is all the requirements for the animation system to work, even external to my actual application itself, we don't need to know how the player is moving or any of that. We can encapsulate it quite nicely into the plugin and include that into our game. This is all then nicely moved into its own animation module inside of our application, making it much easier to understand and maintain the application. Once all our animations are nicely wrapped up into a plugin, we can move on to using external plugins that may have much more advanced functionality that we want to use in multiple applications and don't want to necessarily have to write ourselves, either because we don't understand or because it is highly error prone. The first external plugin I'm going to use is the Leafwing Input Manager. To include this plugin in my game, I need to include the appropriate crate in my dependencies. For the scope of the tutorial series, I will simply importing the star version, since the actual implementation version of the Input Manager doesn't matter for demonstration purposes. Leafwing's Input Manager takes in a different type of struct than the animation plugin that we just created. It takes in a struct with a generic. This generic is used by the plugin to determine the type of actions that our player can take. Because of how Rust type system and compiler work, you need to include phantom data when using a generic type if you don't want it to be abstracted away and you are not actually containing data of that type. This is why we need to use default in order to construct that phantom data and contain it. Once we have the Input Manager added to our game, we also need to make sure that we include the Input Manager bundle on our player. This will contain the player's map, which is the key presses, and their relationship to the actions for that specific entity, and the action state, which is used very similar to the inputs resource to determine what actions that character is currently taking. A big advantage to using this plugin over, say, the generic input systems that Bevy provides is that these inputs can allow for key bindings to be entity specific, allowing for you to have two-player single keyboard games that have different key bindings per player, but don't require you to write duplicate logic in order to control those players, since each player has key bindings and actions associated directly with the entity that that player is attached to. As you can see for the input map, I'm using player input player 1. The player input is an enum that I've created specifically for my game. If you're following along in the GitHub repository, with the commit that matches this slide, the current actions that the player can do is move left, move right, and jump. Later on, these actions are expanded upon. I have then created a constructor method on the player inputs that creates an input map binding for player 1. This is done by providing the key that the player presses and the action that responds to. This can also be done with controllers and mouse inputs as well, not just keyboard bindings. As far as I'm aware, there is no way to bind multiple inputs to a single action in a single approach. You have to specify the action that each key is bound to every time. There is also a hard cap of 16 bindings being attached to any one action. I believe this limitation is applied to increase the speed at which the plugin can determine bindings. Because it knows there are only 16 bindings, the compiler is now able to unwrap loops and simply return false for all bindings that are not assigned, as opposed to needing to have a variant length for loop, which can be slow. This plugin also provides what it calls chords, which are combinations of keys that need to be pressed and only associate with a single action. This is things such as Control, Alt, Delete, having a different action than Control or Alt or Delete independently. The chord will only fire when all three keys are pressed. For chord conflict resolution, the input manager's default behavior is to pick the longest chord that completely encompasses the shorter ones. If I had an input that happened on S and an input that happened on the chord AS, since the chord S is completely encapsulated within the chord AS, only AS will fire. I do believe that the input manager has other types of conflict resolution, such as potentially firing both chords regardless of if they encapsulate each other. But you would have to look into this further yourself. Once we have spawned our player with the appropriate bundle, we will need to change how our player move system works. Instead of taking in the resource inputs, we will instead expand our player query to include the action state of player input type. This will then allow us to access all the inputs that the player is currently doing, and have different inputs depending if we have multiple players. The API for using the action state is almost identical to the inputs resource. The only thing it is missing is the AnyPressed equivalence. This means you'll have to do a logical comparison if you want to continue using the logic of if the player is going left or right, since there is no way of checking those as a single action. Although there is nothing preventing you from creating an independent action called player moving that responds to all presses to the left and all presses to the right, this is not recommended since the 16 binding limit will quickly be reached on even very simple games that have multiple ways of moving. It also implies an artificial limit on the number of key bindings that you could associate, such as keyboard, mouse, or on-screen button. So it is best simply to query both movements rather than trying to combine them into a single action. If we now run the game, you'll find that it acts exactly the same as it did before. There is no impact made on the gameplay for the user, but what it does do is cut down significantly on the amount of boilerplate that we need to do, and also the potential chance of errors when we have to constantly type in all the possible keybinds that could result in that action. It also means that if we want to later change what keys do what actions, we simply have to go to one place in our code, which is the constructor for player 1. I also at this point have a small challenge for those following along if they want to try and implement the double jump like you can see in this clip. It uses a boolean to determine whether the player is allowed to double jump, and also uses the grounded check to determine if the player should consume their double jump or not. If you need help, the GitHub contains the code that I'm using in this scene. While you're checking out the GitHub, please do give it a star. It would be much appreciated. With all our player inputs now managed by an external plugin, reducing the amount of code we need to edit and change in order to control our player. Let's move on to adding some physics instead of having to write our own implementation. Rapier is a physics engine completely written in Rust. They also have an officially supported Bevy plugin that comes in two varieties, the 2D and the 3D version. This separates and changes all of the inputs that you need to be relative to the coordinate space that you use. This is different to how Unity uses its 2D and 3D, since in Unity you still have a vector 3 to determine the velocity of a 2D physics engine, resulting in the z vector actually doing nothing. Whereas Bevy Rapier, if you have the 2D implementation, only lets you provide vector 2s, whereas the 3D implementation has vector 3s. Bevy Inspector also has a Rapier expansion, which includes all of the implementations for most of the Bevy traits. This allows you to use either the Bevy editor or just the inspector's GUI windows in order to interact with some of the Rapier features. In order to get the correct implementations, you need to enable the respective feature, either 2D or 3D Rapier. To include Rapier into our game, very similar to the input plugin, we need to include Rapier Physics plugin into our game. This demonstrates the third type of struct that we can use for inserting plugins. This one both takes in a generic, but also provides configuration data. The generic for this particular Rapier plugin I'm using is no user data, which is just an empty struct that represents that you have no custom data that needs to hook into the physics engine. If you had certain systems that required to extract information from the physics engine that was custom by you, you would need to include that struct into the physics plugin here. As you can see, I'm using the pixels per meter constructor. This allows me to provide a scale for the Rapier engine, allowing for me to conveniently control speeds, such as specifying that I want my character to move so fast. In this particular case, I've said that there is 16 pixels per meter, because my character is 32 pixels tall. This is the equivalent of saying my character is 2 meters tall for all units of measurement. I also include the Inspector Rapier plugin, which allows for the inspector to include all of the requirements in order to display the Rapier information in your inspector, and the Rapier Debug Rendering plugin, which will render outlines and boxes on all of my colliders so that they are easier to debug and configure. Bevy Rapier can be a little confusing to implement all the components required to get the physics engine running, since it does not include a singular bundle like most other plugins do of all the required components. Instead, you must work out what components you need access to, such as a rigid body dynamic, which will make our character interact with physics in the world, such as gravity. There is also other variants, such as static and kinematic versions. Velocity component, which is not crucial to actually include, but is required if you want to change or update the velocity via Bevy code, as opposed to allowing Rapier to completely control the velocity. The collider, which comes in many different shapes and types, such as cubic for the current character creator. There is also spherical, capsules, and other types, such as mesh colliders. For our player, I've also locked the z-axis. This is incredibly important for 2D platformer games, since if you don't lock the z-coordinates, if your character walks slightly off of a slope, they will start to roll and fall off of the slope. And this is not desired for these types of platformers. There is also a whole bunch of other components, such as dampening and friction, that can be added, but I have not done so here. If you would like a great tutorial video of how to set up and use Bevy Rapier, along with its custom player controller, Logic Projects has a great video introducing Bevy Rapier. I will have a link to that video in the description. Once we've implemented the Bevy Rapier plugin and added the colliders to all of our objects in the world, and changed our movement code to use velocities instead of absolute movement of the character, we can open up the game and see how it's changed. As you can see, there are only very small changes to how the character acts in the world, but some of these changes can be catastrophic. If I press sideways into a wall, you'll see that my character sticks to it. This is primarily because I'm constantly setting the velocity to 100. And doing so means that the character is pressed really hard up against the wall and therefore does not have enough gravity to slide down. This is not desirable and needs to be fixed by us. So this is an important lesson that just because we're using pre-built code for the actual implementation of physics, we will need to write custom stuff on top in order to get the behavior that we want. To fix the wall sticking, we are going to use raycasting. For those of you aren't aware, raycasting is when you use the physics engine to fire a ray in a straight line and determine what objects it collides with. To prevent wall stick, what we do is we fire a ray slightly in front of the player. If that ray collides with an object, we determine that the player is too close to a wall in order to move forward, and in which case we do not set their velocity. This means if a player does hit and stick to a wall, it will be for a single frame before the physics engine sets the velocity to 0 and they fall down. Inside our new player move system, we need to include the Rapier context resource. This will allow us to do things with the Rapier physics world, such as fire rays or get collisions from the previous frame. The important thing to note here is, if you remember, our collider for our player is 9 pixels away from their center. The ray is fired at 10. This means that there is about 1 pixel that our player can be from a wall before this ray will collide. The ray is fired in the negative Y direction, meaning it is fired from the top of the player downward. The ray is set to travel only 31.9 pixels. This is important since our player is 32 pixels tall and we don't want them getting stuck on the ground. If the ray was to fire 32 pixels, the error in floating point numbers can cause collisions with the ground and our character abruptly stopping. We set the next value, which represents the inside value, to false. This is because if our player collides with an object not all the way at the top, the ray will start inside the object, and Rapier distinguishes between an array starting inside an object and an array entering an object. The reason it makes this distinction is if you have a player with the ray firing from inside of their head, you don't want the ray to collide with the player. You want it to collide with the thing that the player can see. We then need to provide a query filter for the colliders. In this case, we use the constructor for excluding dynamics, and then we also exclude sensors. This means that the player will not get stopped by dynamic objects such as enemies, and also will not stop on things like sensors, since they will not be collided with anyway. So only static objects will be collided with. The exact same code is used for moving to the right, except we offset our ray start position by 10 pixels to the right of our character instead of 10 pixels to the left. As you can see, this now allows our character to collide with the wall without getting stuck to it. This is the desired behavior we want. The only limitation is we need to remember there is a 1 pixel buffer that our player cannot move next to a wall. This means that if you had really high friction on the player and they were running along the ground, they would stop 1 pixel away from any wall. And it would not be possible for the player to get to the wall. But when we are jumping, this 1 pixel gap does not matter because the character will continue with their momentum into the wall, clearing that 1 pixel gap. For the rest of this video, we'll be working on implementing new features into this game, as opposed to implementing and using plugins to cover the systems that have already been used. The first of these new systems that I want to implement is auto step. Again, we will use raycasting to determine how the player should auto step. For those that don't know, auto step is when a platformer allows you to walk into slightly short objects and your character automatically step up onto them without needing to jump by the player. Some games implement this system by causing the player to automatically proc their jump when the player is so close to a block. Think of games such as Minecraft. This, however, can be quite infuriating because when the player is jumping, they are no longer able to jump themselves, and the auto jump is not very good at actually determining when you need to jump to get onto a block. This can result in if you walk diagonally next to a block, your character constantly jumping without actually landing on the block they're trying to jump onto. So for my game, I'm taking the approach of simply teleporting the player slightly higher than the block when they run into it, so that if they are moving forward, they'll fall onto it. For the auto step, I've decided to make my players automatically step up onto any block half their height. Anything taller than that, and the player will simply walk into it. Anything lower than that, the player will teleport on top of and keep walking. In order to do this properly, there are a few things we need to do. The first is fire a ray to determine if the auto step needs to trigger. This is done by offsetting a ray the same as we did for the wall collision, except we want it to be at the player's chest height, just slightly higher, again for rounding errors in floating point numbers, so any object below the player's chest height will be auto-stepped onto. We continue to fire the ray down since we only care if the object is below the player's chest, and we fire the ray 15.9 pixels down, again so that the player doesn't auto-step on the ground. This wouldn't particularly matter with how I implement the auto step height detection, but we don't want this system firing every single frame since that is a waste of compute. For this particular case, we have to set the next flag true. Unlike the wall detection, we do care if the ray starts outside of the block that we are trying to step on. Otherwise, any block above the player's chest height would proc the collision, since the ray was inside it when we started. The true here will mean that the ray must have originated outside of the collider before it to detect. We then use the same query filter of only colliding with static objects. The next step is to check to see if we got a collision. The cast ray method will return an option containing the first entity and the distance that the ray traveled before colliding with it. For this system, we deconstruct this in an if-let statement so that if we didn't collide with anything, we don't run any auto-step checks after that. The next thing we need to do is determine if the player is able to auto-step because there is nothing above them. If we don't do these checks, it is possible that the player will attempt to auto-step into a block above their head, if there is a block. The way I've gone about this is somewhat naive, since I simply cast 2 rays up. The alternative would be to cast a shape up, but I did not want to expand too much on the API covered in this video. For the 2 upward rays, one is set slightly in front of the character, and one is set slightly behind the character, right at their head level. This ray, as opposed to all the other rays we've been firing, is fired upwards, 32 pixels. This is the height of the player, which means that if the player cannot fit through the gap directly above them, they will not be moved up. We again make sure the ray will not hit the player themselves when fired up, and will only hit static object. We then check that both of those rays did not collide with anything, and that the player is currently on the ground. If that is the case, we move the player up 16.1 pixels minus the distance the ray fired downwards was from hitting the ground. We move 16.1 pixels because that is enough that at the absolute maximum height the player will step, they will step 1/10 of a pixel higher. So if they are currently moving sideways with their velocity set to greater than 0, they will glide onto that block without jittering up and falling down. The reason we subtract the distance the first ray was is not all of our steps will be exactly 16 pixels. So if you had a step that was half a block tall, so 8 pixels, the ray would say that it hit at a distance of 8. This means we want to step up only 8.1 pixels, not the full 16. The exact same code is duplicated when the player is pressed. The exact same procedure is followed when the player is moving to the right, except we need to invert the offset of the ray to be out the right side of the player instead of the left. As you can see, our auto step works lovely in this clip as our player runs back and forth up and down the steps without any noticeable jitter or jumping around from the player being teleported. Another reason to make the player teleport the height as opposed to just applying upward velocity so that the player would jump onto the step. To do this, we would need the ray that detects the step to be further out in front of the player in order to give the player time to move upwards without colliding to the box. Or we would have to remove some of the logic that controls the player's sideways motion. Now I'm going to move on to showing you how I implemented my map spawning plugin that allows me to create the world that you see the player running around in. This is first done inside the plugin, where we will initialize the terrain sprites, which is simply just a resource that holds the handle to the texture atlas that contains all my sprite maps. We then add an event that is all the events that I want to do in the world, such as spawning pits of terrain, or in the future, spawning enemies or collectibles. The struct that we use as an event is simply an enum that needs to implement send and sync. But that is the only requirements on what struct you can use, is send, sync, and static. We then add a system that will spawn the objects in the world, so it will consume the events sent, any spawn-related events it will deal with. We then initialize the map data resource, which will be a resource containing any information about the map that may be required for spawning the objects, such as if we want to spawn something randomly in the world, we want to make sure that that map cell is empty before attempting to spawn. We could do this with the physics world by doing a collision detection, but in this case, we may have other information that won't be so easily attainable that may need to be stored in the map data. The only map event that I've currently implemented is the spawn map event. This takes in a boxed map object. Each boxed map object contains a spawn method, which takes in the terrain sprite, the command so it can spawn itself, and access to the map data that it can edit and manipulate. The spawn function for the map box that I have implemented, which is the only shape that you can currently spawn into the world, matches the width and height of the box. If it is a 1x1 box, it'll spawn it at the appropriate offset calculations with the appropriate 1x1 collider and the single box sprite. If, however, the box is 1 high by any width, it will calculate the appropriately sized hitbox and position to put the transform. But when it spawns the sprite for this box, it'll do it as children, inserting a left-ended sprite at the left end, then the center joining sprites until it gets to the right end, and then put the right ending sprite. This exact same code is duplicated but slightly modified for the any extra length side that has a width of 1. And finally, the only other shape that you can do is a 2x2 box, since this has a custom sprite. Any other size, such as 3x3, can't be created using the sprite sheets that I'm currently using. but the logic for those would be fairly simple to implement if your sprite sheet enabled them. For each cell inside the shape, checking its position. If its position was 1, 1, spawning the top left corner. If its position was max x1, spawning the top right corner. If its position was 1 max y, spawning the bottom left corner. And if its position was max x max y, spawning the bottom right corner. And then spawning the appropriate edges and center fill. Again, by following the logic of if the appropriate edge is met, spawning that edge, otherwise spawning infill. Our spawn objects system simply consumes all of our events, and if they are a spawn event, calls the spawn method, providing it the appropriate parameters. This easily allows us to specify maps that are on a fixed grid, since the player can only specify integer values for the size and position of the blocks, which we then convert in code to float. The map creator is not possible to place blocks at half points. This doesn't mean that half blocks aren't possible, because as you can see here just above my player, there is a half block. This is because one of the pillars is 4 high and the other is 5. Because of how I'm determining the colliders, the odd number results in a half movement instead of a full movement. This is a bug that I've been trying to fix, but every time I get it working, it breaks other things. This is also a great opportunity to show off the anti-head bonk, since the character will auto-step up the stairs, but won't auto-step into the block. If you don't do the head bonking, the character will get stuck in this block, since they will be teleported up into it, and be able to stand on the future block here, but be stuck inside the previous block. That concludes the programming section of this video. For the rest of the video, I'm going to cover what I intend to add to the game in order to make it somewhat fun. I've found during the development process that the most fun I've had playing the game is trying to collect the collectible as quickly as possible as it randomly teleports around the screen. So for the rest of this series, I am planning to implement basically the equivalent of a snake game, using a 2D platformer instead of a fixed grid. The idea of this game that's going to make it novel and unique is that the player will spawn at the start position, and every time they collect the collectible, a new player will spawn at that start position and follow the exact set of movements that the original player moved. If the player collides with any of the following ghosts, they will die. This will result in you having to plan out how you intend to move in order to give yourself the ability to go back that way. The ghosts will never disappear. Since they are following a continuous stream of inputs from the player, they should be able to infinitely continue following the player until eventually they catch up, because the player has to stop and wait for a previous ghost to move past, while sometimes ending up stuck for too long that the previous ghost will catch up. As you collect more and more collectibles, more and more ghosts will have spawned. This will make it harder and harder to avoid ghosts. Another system I intend to implement for the ghosts that I have somewhat implemented already is the ability to change which character you are currently playing as. Each player may have different abilities, such as, one having a double jump or something like that. And my player has fallen off the screen, so don't mind that. But I was thinking that as long as you are in a different player form as the ghost that you collide with, it doesn't kill you. So you basically have the equivalent of changing players in order to move through a ghost. But you need to be careful, because the ghosts will also be changing player whenever you change player, which means at some point it will be impossible to move around the screen, since all 4 possible player states will be taken up by ghosts moving through the screen. The simple character changing was just a way of allowing the player to go, oh crap, I need to basically use a life in order to get through here. And you may then change back to the original character, or you may have to continue running around, and just add to the chaos and complexity of you may have to change players in order to cross a path and then change back to cross a different path. And I think this could be quite interesting and exciting. So if you are looking forward to seeing me implement this all in Bevy, then please do like, comment, and subscribe. And don't forget to check out my Patreon for the opportunity to have your name mentioned in the video. And I would really appreciate the support in the channel. All money that goes to my Patreon, at least for the very beginning, will be fed straight back into the channel, such as hiring people to create thumbnails and stuff like that, because I'm really bad at it, but it would be much appreciated if you could support the channel. Thank you, and I will see you next time.